Hello.
Hello, everyone. Hello, everyone. Yeah. Good afternoon. I'm Amin Zarei, Research Fellow at the University of Saudi. It's my pleasure to be the chair of another session that dedicated to early career research that works under umbrella of the AI for Net Zero, Artificial Intelligence for UK Net Zero Emission, that's funded by UKRI. So today we are delighted to host two speakers, Dr. Goyal and Dr. Ollie Hardy. Please join me welcoming and feel free to welcoming them and feel free to engage anytime in discussion by writing your comment and question. We have 10-minute Q&A at the end of each talk, and you can just leave your comment and question as well, and the speaker answer it. But before I start the first talk, let me remind you that to leave your comments, you need to log in on your Google account. So please do that before to leave your comment. So without any delay, let me introduce our first speaker of today, Dr. Goyal Angwan. She holds a PhD in electrical engineering, and she is currently a PDRA at Northumbria University. She completed her doctorate from the National Institute of Technology in Raipur in India, if I pronounce well, with a specialization in microgrid protection. So thank you for your for joining today, and the floor is yours.
Yeah, thank you, Ami. So, hello all. I am Dr. Goyal Awagan, and I am a postdoctoral research associate at Northumbria University. And today I will be presenting on hybrid microgrid protection. Basically, I will be speaking how to enhance the resilience to network topology changes and weather intermittency. So this is the part of the project, that is the VPP WARD project, UKRI funded VPP WARD project, that is virtual power plant with artificial intelligence for resilience and decarbonization. So this is my brief introduction, which is Annie has already described. So moving ahead, this is the outline of my presentation. So first will be the research background, followed by the formulation of the optimal sensor placement problem. Then comes the solar irradiance intermittency modeling. And the fourth one is the LSTM-based protection methodology, followed by performance analysis and conclusions and future research directions. So to talk about this topic is that the current power generation industry has experienced a paradigm shift, particularly from the centralized generation to distributed generation, and it has led to the adoption of microgrids. So microgrid can basically be described as a combination of distributed energy resources and interconnected loads confined within specified electrical boundaries. Moreover, the adoption of the global initiatives related particularly the net zero carbon emissions and the electrification of transportation has also led to the massive deployment of distributed energy resources. So basically, based on the voltage and current nature, so the microgrids are basically classified as AC, DC, and hybrid. So, although this hybrid microgrid or the adoption of microgrid has a number of challenges, the acceptance of hybrid microgrid has been hindered somehow due to the challenges in developing a reliable protection scheme. So, the first challenge relates to the presence of both AC as well as DC microgrids, as you can see in figure 1. So, due to the presence of both the microgrids, there is variability in the nature of signals acquired from different buses. Also, the need for adaptive settings. As you all know that microgrids operate in two different operating modes, that is the grid connected mode and islanded mode. So the need for adaptive settings is one of the primary challenge, and also the low magnitude of short circuit currents during the islanding mode. All these factors somehow hinders the protection scheme, that is executing the protection task. So the motivation behind carrying out this research work is mainly because the low magnitude of fault current, as I've already talked, this makes the detection of high impedance fault challenging. Also, the second factor is the stochastic variation in the operation of PV-based DERs. As the nature of PV-based DERs is variable due to the weather intermittency, and also the network reconfiguration is also the another cause. So all these factors has led for carrying out this work. So as you can all see that in figure number 2, figure 2a, here we can see that these two waveforms are for the same irradiance level, that is 1000 watt per square meter. But the first waveform is for the low impedance fault, and the second waveform is for the inception of high impedance fault. So as we can see that during the inception of low impedance fault, there is a relatively higher magnitude of current, and so we can differentiate between the instant before the fault and after the fault. However, in case of figure 2b, it is very difficult for the threshold bit settings to differentiate between the inception of fault. So this is one of the case. And also in figure 3, there is a waveform with different irradiance levels. So first one is the no fault case with higher irradiance level, and the second one is the fault case with low irradiance level. However, the nature of currents is same, so this can lead to mal-operation of the relays. So the ultimate aim of talking about these two figures is that uh, differentiating between the high impedance fault is very difficult using the threshold based relays. So we have to go for some artificial intelligence based schemes. Particularly in my work, I have used the LSTM classifier. So the main contributions of my work is that I have designed a LSTM based approach for the protection of hybrid microgrid, which is sensitive to high impedance fault. Then the second contribution is regarding imparting robustness to the hybrid microgrid protection against network reconfiguration, basically the line outages arising due to the N-1 contingency. And the third point I have discussed is imparting immunity to the high impedance fault detection against the weather intermittency by incorporating the statistical modeling of solar intermittency using the meteorological data, particularly from the NREL data. And also the fourth task is that I have the redundancy in the sensor information has been avoided by identification of the critical sensor sets. So this is the main AC/DC hybrid microgrid system which I have considered. As you can see that this is the microgrid system which is connected to the utility grid at 69 kV 60 Hertz, and it comprises of three subgrids, that is the AC microgrid 1, AC microgrid 2, and the DC microgrid. AC microgrid 1 here particularly has one diesel generator as a DER, and AC microgrid 2 has two DERs, that is the battery energy storage system and the PV, whereas the DC microgrid has another battery and PV. So this is the microgrid system having a total of 14 buses, 17 buses and 14 lines. So this is the modified IEEE 14 bus distribution system considered in the study. The first part is the formulation of the optimal sensor placement problem. So talking about the optimal sensor placement, as we all know that the placement of sensors at each and every bus in the microgrid is often not feasible due to the requirements of communication infrastructure. So here we consider the optimal sensor placement problems. The optimal sensor placement problem aims at minimizing the sensor installation cost. So as you can see that in equation number 1, CI is the cost associated with the sensor installation. subject to some constraints. So FIL is the observability constraint for the installation of the sensor at the ith bus during the outage of line L. So this is the OSPP considering the optimal sensor placement problem, considering all the n-1 contingency scenarios. So after analyzing or after formulating this optimal sensor placement problem, we have found that it is not necessary to place the sensor at each and every bus, that is the 17 buses in the system, but we can place only at 7 buses. So there is a considerable reduction in the sensor installation cost by almost 59%, as you can all see in table number 1. So this is the advantage, or this is the usefulness of carrying out the optimal sensor placement analysis in this microgrid protection scheme. Then next task is the solar irradiance intermittency modeling. So to incorporate the solar irradiance intermittency present in the PV-based TERs, we have considered the annual data, that is particularly the global horizontal irradiance across a particular region, that is the Chile region in South America, with some hourly resolution for a particular year, that is the 2020. So as you can see in reference number 2, the data is available on the National Renewable Energy Department website. And the annual solar data is taken in the range of 100 to 1000 watt per square meter and has been fitted and modeled using the Gaussian distribution function. So the equation 6 is the normal Gaussian distribution function, where capital G represents the irradiance level and sigma is the standard deviation of the probability distribution function and mu is the mean of PDM. So by modeling the Gaussian distribution function, then this solar irradiance probability distribution model is incorporated in the training data set of the LSTM classifier. So moving further, I will be discussing the flowchart of this LSTM based microgrid protection scheme. So the protection methodology can be basically divided into 4 parts. So number 1 is the optimal sensor placement problem. Number 2 is the solar irradiance modeling, as we have already discussed. And the third part is the extraction of the current signals from phases A, B, and C from optimal sensor play set. And the last one will be designing the LSTM modules for the protection task. The number 1 task will be the fault detection task. The number 2 task will be the fault classification task. And number 3 task will be the faulty line identification task. So from LSTM2, the relaying means considering the output of LSTM2 and LSTM3, that is by knowing the fault type and the faulty section, the relaying decision will be taken and the trip signal will be given to the circuit breaker. So the performance analysis has been carried out by considering the operating scenarios mentioned in table 2. So the simulation model, that is the hybrid microgrid discussed in figure 1, has been simulated for different operating parameters, like by varying the fault resistance, fault inception angles, the fault location, global horizontal irradiance, and we have got a number of training and testing scenarios for both the fault cases and no fault cases. And as you can see in table number 3, the performance of the proposed fault detector, that is the LSTM1, for both low impedance fault and high impedance fault. So we can see that the proposed scheme is able to detect the fault cases accurately, achieving a overall accuracy of about 99.69%. So next is the performance of the fault classification module, that is the LSTM2, with the other classifiers, particularly the CNN, convolutional neural network, and the ensemble subspace KNN classifier. As we can all see that the proposed classifier is able to achieve an accuracy of 99.6% as compared to the CNN and ensemble subspace classifiers. And also, as in table 5, the comparative analysis of the LSTM-based classifier has been carried out with the other protection techniques, considering some reliability indices, that is the dependability and security. So the proposed scheme has achieved a good dependability of around 99.73% and security of 99.29%. So the main factors are the dependability and security achieved for the proposed scheme. Moving ahead, the performance comparison of the proposed classifier has also been carried out with the other classifiers in terms of faulty section identification module. So the proposed scheme has achieved a good accuracy in terms of section identification, which comes to be 99.56%. The performance analysis of the proposed LSTM-based scheme in terms of the fault detection accuracy has been plotted here through the 3D plot, and it gives a good fault detection accuracy, and similar is the case for the fault classification accuracy. So here we have considered the irradiance of PV, as we have two PVs in our system. So we have considered the irradiance of PV1 on one axis and PV2 on second axis, and then tried to plot the fault detection accuracy and fault classification accuracies. Next, the performance analysis has also been carried out for the inception of both HIF, that is the high impedance fault. So as we can see that the current waveform at bus 2 with two different irradiance, that is 1000 watt per square meter and 400 watt per square meter. Though there is a huge difference, one is for the high irradiance level and the second one is for the low irradiance level, the response of the LSTM classifier is satisfactory. That is, the trip signal is generated within 15.6 milliseconds for the first case, and for the second case, it is generated within 16.5 milliseconds of the fault inception. Also, as in figure 10, we can see that the current waveform is for the irradiance 1000 watt per square meter and 700 watt per square meter, but for the low impedance fault. In this case also, the proposed classifier is able to generate the trip signal within the time specified. Also, the performance analysis has been carried out for the outage of line L. That is, during the network reconfiguration, means there is a outage of line S14 followed by some high impedance fault. However, we can see that the trip signal is generated within 16.4 milliseconds of the fault inception. Also, the performance of the protection scheme has been analyzed for the non-linear loading conditions, and we can see that the trip signal is generated within 7.3 milliseconds of fault inception, as in figure 12b. And also, the performance has been also carried out during the noisy signals. So the performance has been tested for the noisy signal, that is the white Gaussian noise of around 10 dB. So we can see that the output of the fault classifier is within the limits. So we can see that the proposed scheme has performed reliably during the noisy conditions also. So to conclude with, these are some of the conclusions. As we have seen that there has been a considerable reduction in the sensor installation cost, that is almost 59%, and communication infrastructure by considering the optimal sensor placement problem, including the N-1 line contingencies. And also, there has been immunity against the weather intermittency using the statistical modeling of the solar intermittency of the NREL data. And the proposed LSTM-based HIF detection scheme is able to achieve all the reliability indices with robust to both the weather intermittency and also the network reconfiguration, that is the N-1 line contingencies. So these are some of the future research directions that the proposed work can be implemented on some co-simulation framework. And also we can explore the feasibility and applicability of the proposed protection scheme with the wind-based DER integration. So this is my presentation. So yeah, thank you.
Thank you. Thank you, Goyal, for your valuable presentation. And also, we have time for maybe 20 minutes for Q&A. We would appreciate if you leave your question and comment. Before that, I should apologize for didn't introducing Dr. Ahmed Sheikh, that he's helping me in co-chairing this session. Sorry for not introducing at the beginning.
No problem. I'm here only to support if there's technical difficulties and ask questions. Very good talk, Goyal. Thank you. And I don't see any questions, so I will start with the question. Goyal, very interesting talk. It's really timely topic, and it's very important as we know the grid we currently have in the UK is not ready for adoption of renewable resources. In terms of accuracy, your model have improved the accuracy from 97 to 99.
Yes.
Could you elaborate on these cases which are missed? What kind of methods where LSTM methodology is able to predict and CNN-based techniques fails? And the second question is about how do you prepare your training data? Because probably you prepare your training data.
Okay.
Because this training data is I didn't get from the question from the presentation. Was it like artificially generated based in simulation packages with some real data sets, or was it entirely real data sets? I didn't get that.
Yes, sure. So shall I go back to my slides? Yeah. So first one is regarding the data generation. This is the hybrid microgrid model which I have simulated in the MATLAB Simulink platform. So this is a very used system. So here we can see that there are around 14 lines and 17 buses. So suppose we are taking line S1. So it will have certain length, and there is the possibility of creating lot of data in that line. Means we can vary the fault resistance, the fault inception angles, and also the length of the line. And so the number of scenarios can be generated. And also this is the case of the contingency. So the data can be increased further, because here I have considered, suppose there is an outage of line S1, then I can consider the data generation in the remaining of the lines. So similarly, one by one, I have to consider the outage of one lines. And so the huge data has been generated for both low impedance fault and high impedance fault cases.
Thank you. The other question is about where is the accuracies between the different methodology. And
yes.
It's 97 versus 99. Where does a different LSTM capture, or what cases LSTM is able to capture and CNN is not?
Yeah, in case of LSTM, here we have different gates. That is the forget gate, the input gate, and output gates. So in LSTM, we are giving in the form of some series. So it is able to remember that data and carry on the further process. So, and in case of CNN, whereas we are giving in the form of some what you say, the pictures, the pictorial form. So in that case, I have tried with CNN also, but in case of CNN, I've got the reduced accuracy. But in LSTM, somehow the gates and the encoders have come. So it is better able to remember the previous data and carry out the analysis. And so the LSTM gave me a far better accuracy as compared to the CNN.
Thank you.
Thank you.
I think we still have time for a couple of minutes. If any question comes up, we can answer. Also, I have a question about the historical data. Could you please let us know about the resource source of your data? I mean, your for LSTM.
Okay. Can you just repeat?
Where is your? I mean, from where you got your data for LSTM for using in LSTM?
So I didn't get the data. I have generated the data for this model in the MATLAB platform.
And then use it in LSTM.
Yes, I have acquired the current and voltage signals from each of the buses and then given as input to the LSTM classifier for the training.
Thank you.
I will ask another question while we are waiting for more questions. So this is a question more general about application of artificial intelligence in grid management in general and microgrid. So what you are doing, if I understand correctly, this is fault prediction, which is like predictive maintenance application. You are predicting where the fault, when it will happen, and is a place where have you or your team worked on prediction tasks, which could assist, like fault prediction? This will be like an alert system, or will it help in the design of more resilient grid network? And the second thing, can we use LSTM for supply and demand curve prediction? Is that
saying to be a prediction problem, this is basically a classification problem in the area of protection. So when we design a protection scheme, what we do is we take some previous data set and try to see that whenever the fault comes in the system, so the system has already been trained to differentiate that fault from the healthy condition and the faulty condition. So rather than saying it to be a prediction problem, we can say that it's the classification type of problem. So the classifier has been used. Yes. Yeah.
I think we don't have any time for now. So thank you for your presentation, Goyal, and hope we'll see you again for your to present your new result in the future.
Thank you. Thank you.
Thank you so much. So the next presenter, Dr. Ollie Hardy from the University of Lincoln. He's a PDRA in Intelligent System and Lincoln Institute for Agri-Food Technology. His research interests are creating databases for and form robots in agricultural context. And today he will present about the robotic phenotyping, if I'm reading correct. Yeah, to accelerate the building of the mechanism as the net zero biofuel. So thank you for joining, and the floor is yours.
Thank you very much. Hello, my name is Ollie Hardy. I'm a PDRA in Intelligent Systems at the Lincoln Institute for Agri-Food Technology. I'm presenting today some work that was completed as part of an ESRC project funded for ourselves, the University of Aberystwyth University and the University of Southampton. So our actual project name is Plant Selection and Breeding for Net Zero, a collaboration between these three universities led by Aberystwyth University. But we internally refer to this project as Miscanthus AI. So what is Miscanthus? Miscanthus is a C4 perennial grass, which means that it's very efficient at photosynthesizing and will do well in sort of hotter climates. so well suited for climate change. It originates originally from Southeast Asia. You might have seen it grown as a decorative plant. It's a very hardy plant and grows on marginal soils, which means that you could grow this instead of on pristine agricultural land. You could grow it nearer to a power station, which would make it advantageous as a biofuel. There's different varieties that are either grown from rhizome, like ginger, not rhizome is ginger is an example of rhizome, or seeded varieties, and it's low input. So once you've got this established, after about 2 years, you can have 25 years of product. It's weed tolerant, it's not, and you don't need to fertilize it. And what makes it so good as a biofuel is that it can actually grow to over 3 meters in height with a bamboo-like cane. So this is it early in stage, and this is it almost ready to harvest. So this is when myself and my colleague went out there to take some samples. I've got a piece here. So really nice bamboo-like material. You can chip this up and turn it into a variety of different fibrous-based products. But one of the key advantages is burning this as a biofuel. So because it's a perennial grass, you establish it and you're putting carbon back into the soil without having to continually retill and replant. And then when it goes up and forms this sort of lignin-based fibrous cane, you can chop that down, burn that, release some of the carbon back into the atmosphere that you then capture next year as it grows back up again. And so you have this net zero biofuel that you can grow much closer to power plants rather than importing wood chips from America, for example. So why do we need to breed new forms of Miscanthus? Miscanthus is not a domesticated plant in the same way wheat is, for example. And plant breeding is a long, manually intensive process. It can take 10 to 13 years to introduce a new variety of wheat, for example, which is not just all the testing, but also, which is not just the growing process. You need to be able to show through tests that it's distinctive and stable. And for Miscanthus, there are multiple traits that would be desirable in a commercially available crop. So just an example of plant breeding, I've shown some ancient corn here, and then our contemporary corn. And this has taken thousands of years, but maybe we're looking at accelerating a 20-year breeding process into maybe 4 or 5 years for Miscanthus. So here are a variety of the different traits that Miscanthus plants could be scored on by plant breeders. So of course there's height and fresh weight and dry weight, but then also if you want to look at it in more detail, people take dry weight of the stems, dry weight of the leaves, how much light is getting through the canopy, manually scoring on frost damage, the transect density, how green is it? And this is just a small sample of some of the different traits that we've seen collected by plant breeders to make a decision on which Miscanthus lines should be taken through to the next generation. So how can we use AI to expedite this process? And so within our project, we have 3 different work packages. We have a work package where we're using machine learning and statistical models for genomic selection. So we take a nice historical data set of genomic lines and use machine learning and statistical model techniques to understand the connections between the genetic information and the traits that we want to see. So I've given this a very crude simplification of this is trying to understand what we should be growing. And then my work package that I'm going to speak about today, which is data acquisition and in-field phenotyping. So how can we observe the plants that we've selected to grow? How can we get this information on all the different traits, but much faster and with less manual input? So I've simplified that down to the process of how is it growing? And then we also have a really nice unique aspect of explaining and adapt, which is applying argumentation to support the decision-making process. So plant breeding is it's something that we can augment with automation, but it's not something that will ever replace the humans in the loop because it's so much about experience. And it's the sort of thing where if I gave a plant breeder a list of here's all the categories that I think, I've collected them with my robot, this is the one, they would still tell me, okay, but I want to go have a look before I select it. And we want to make sure that we can help phrase their decision process in this formal computer format of using arguments to say why you would pick this one over another. And Miscanthus is a really good plan for this because it's new to this plant breeding process, so we've got a chance to really integrate our process into here, and if it's successful in Miscanthus, perhaps we can apply it to more established crops. So focusing on our data collection work package, we're picking sort of one key trait, which is cane height, so how tall our Miscanthus is growing, and linking that to the biomass, because ultimately this is something that's going to be harvested and burnt. The taller your cane, the more material you have to burn. Arguably, that one would be a better fuel. And we're autonomously collecting this data throughout a whole Miscanthus growth season, so from the earliest shoots through to ready to harvest large canes. And we're also supporting our autonomous data collection with a process of ground truth data collection too. So the workhorse of our data collection is this DJI M300 drone, which we've got equipped with 2 different payloads, Zenmuse L1 LiDAR and a Miscanthus Red Edge, which is a multispectral camera that collects red, green, blue, near red and near infrared. Sorry, red edge and near infrared. So we can extract things like NDVI with that data. The drone and the camera, it can only carry one of these at a time, weighs about 7 kilos. So you actually need a special license to be able to fly this drone. And it's, for this equipment together, it's about £24,000 for one camera and the drone. So it is an off-the-shelf solution, but it's a very expensive shelf. The drone is a really nice piece of kit. It can fly for up to 45 minutes of flight time. Of course, that's dependent on your weather conditions. It will be reduced in windier conditions and also with a heavier payload. And it also has a number of sensors on it and RTK, which is real-time kinematics and flight planning modes. So we can set out a set of waypoints to map a field, tell the drone to go, and it will go off and start collecting data for us. So a really nice piece of kit, but an expensive one, and one that you need to be very careful with. And so here's an example of some of the data that we can collect from this. So this is from our LiDAR. So below is an RGB image of a set of 9 different Miscanthus plants captured from the drone at a height of 15 meters. And above this is a 3D reconstruction that we've got with the LiDAR. So as it's flying over the plants, it's continuously bouncing a laser, and it counts the time very accurately to how long it takes for the laser to bounce back, and uses that with the RGB images to reconstruct a full color 3D model. And this is from the ground, but it's with our Miscanthus Red Edge, and so we can collect multispectral imaging and give ourselves an idea of NDVI. And I think later on in the project, if we can combine this NDVI data with our 3D models, we'll get a really good understanding of height and biomass all through drone collecting, rather than going out and manually having to measure a lot of tricky traits. So for this process, we've got 3 different test sites. So our first site is operated by a company called Terravesta, and they're in Lincolnshire, about 10-15 minutes north of us. This site is about a 95 by 180 meter plot of Miscanthus. Individually, there are sets of small test plots that are 7 by 4 meters across, and a set of much larger plots, 80 by 10 meters across. These plots have been grown for over 10 years with a mixture of seed and rhizome-based Miscanthus plants here. And we've been given access to 7 different genotypes, which apologize to anybody who's colorblind, but I've got listed here in different colors. And each time we capture one of these on a LiDAR mission, the drone flight takes about 23 minutes to cover this whole area. It captures 346 images. They're nice high resolution images, 8.7 megabytes each. And we use that to create a .las file, which is this 3D model, which is a large file, it's 9.6 gigabytes. And we flew this drone at 15 meters of height. You can fly the drone a bit higher and capture more per area, but you will lose a bit of resolution. And it's a trade-off between how can you cover the most field on your limited battery time and still get a nice high resolution 3D model. Our second field site is a Truscoid in Aberystwyth. This is another well-established plot, and they've got even more genotypes, but there are at least 5 in common to our Lincolnshire site. So for at least these 5 genotypes, we can have a comparison of how they're growing all the way over here on the east of the country and right over on the west coast of Wales. So really nice separation between the two, and see how they grow in these different environments. So we've got here 2 different LiDAR maps. This is when it was right just after it was cut, and this is several months later when it's starting to re-emerge. And we also have one additional site, which is in our walled garden on our Rhizome campus at the University of Lincoln. This is a vegetable garden that we have on campus, and we've got 5 Miscanthus plants growing individually here, and a plot about 1 by 2 meters of Miscanthus growing at the back. This is really nice because we can go out with much greater frequency to capture data, and also because we've got single plants spread out, we can get a better view of the size of the plant and try and understand some of the other things that can be captured from this phenotypic data, for example, angle or stem thickness. So when we go out and capture a LiDAR mission, we have this data processing pipeline. We plan the mission. That's done in the drone software, which is DJI Pilot. We only have to do this once for the field, because once we've programmed our mission, then we can refly it every time. So our first mission was a little bit tricky, but after that, we were going out and check everything's good to go, set up the drone, and we know that it's going to fly and map our location, and we can compare this over time series, knowing that they followed the exact same plan. So after, we plan our mission, then we fly each time. Then we have to take the data back and create a LAS file. That is one limitation of this drone, is that there is proprietary software to create the 3D map. But once we have this LAS file, which is created from the IMU data, the RTK data, and the RGB data, we can then take that and convert it into different, more usable forms. So we convert our LAS file into a PLY file with real-world coordinates using Agisoft Metashape. And then with the PLY file, we can run different processes, compare the different maps, and extract data from that. So that's one of the processes we're going through at the moment. And in support of our LiDAR data, we've got ground truth measurements. So for this year's growth, we're planning to capture monthly throughout the 2024 to 2025 season. And each time we go and fly our drone, we take an average, we take 10 canes per plot. So we physically cut them down, and then we can measure cane length, the dry weight by chopping it up and putting it in an oven for a few days. We measure the number of leaves, and we measure the number of green photosynthesizing leaves to brown leaves. And we also measure the leaf area using this piece of equipment, which, I don't know if you can see my mouse, using this piece of equipment on the right-hand side, which is a portable leaf area scanner. So much like a printer scanner, you pull the leaf through it, and it records the area view. And we've also taken a 25 centimeter by 25 centimeter transect, so we can relate all these measurements to transect density. So far, we've got 3 measurements that we took from the end of last year's season, which just happened to be how these plants are continuously growing, but when we were able to actually get the drone up and out there. So we only caught the back sort of third, I guess, of the growth stage of last year's Miscanthus plant. But this year we've managed to get it from freshly cut through to hopefully the fully senesced stage. So we got 3 from last year, and so far we're on track for having 4 this year. And this is an example of a height map that we've created from our PLY data. So this is when it was in the sort of the end of summer, start of September, really nice, fully grown. Then as it starts to senesce, the plant's got a little bit bigger, but you can see a little bit more patches. This is fully senesced when it's ready to chop. Instead of having these nice big bushy green things, we've got a lot more like canes just standing in the field. And then this is after it's been completely harvested, and these little red dots are the bales that they've been baled up into to be taken away as fuel. This is later in that month. We've got a few little emerging sprouts, and then we start to get back into observable thickness. Something interesting to see on this is that there is a little border around the top section, which is where larger Miscanthus is grown to protect the test plots inside. So there's lots of little filtering and things we need to do to consider how we would measure this. Sorry. Oops. Yeah, and this was created by, these maps were created by a colleague of mine called Yusu. And I just want to show you some nice images that we've captured in the Miscanthus. So this white part in the top left-hand corner is a weather station, and it's a really nice marker so we can compare multiple different time series images. So here we have a plot of 9 different Miscanthus varieties. This is at its peak growth when it's the biggest, bushiest, greenest. Then we see the real differences start to emerge as they senesce. So some senesce much faster than others, so they've gone a lot browner, lost their moisture content, and that might be more favorable for some farmers and producers because that means they can get to harvesting it sooner. This is it just before it's ready to be cut. I think this was maybe a week before it was cut. And there's these really thin skeletal poles, canes standing up. All the greenness is gone, and this is ready to be harvested down with a conventional sort of threshing machine. This is shortly after the harvest. You can see again they've got the bale there, and everything is gone apart from some remains that they kept around the weather station because it was a bit tricky to process around there. But that was on the 10th of May, and this one's on the 28th of May. So 2 weeks later, we start to see emergence. By June, we're starting to actually see significant differences in the different plants. And by July, we've got almost half the height that they're going to be by fully grown time. So what's next for this project? We're going to continue to capture data through to the senescence, which is March 2025, which also coincides with the end of this project. So we should, within this project, be able to capture a nice end-to-end Miscanthus life cycle. With this data set, we want to make it publicly available after completion of the project. And now that we have all this data and ways of capturing it, we want to explore methods of extracting more accurate height data from our point clouds. And also, within our remaining time, explore what other phenotypic traits we can extract from the data. Okay, thank you very much for listening.
Thank you, Ollie, for your presentation. That was so exciting about it. We have about 10 minutes. Please share your comment and question in next 10 minutes so Ollie can answer it.
I will start again. Thank you, Ollie, for the clear presentation. Very, very nice presentation. I have a question. Are you collecting weather data, precipitation data aligned with the growth kind of or moisture in the soil as well?
We could probably access the information, but we haven't been collecting that information. That's true. It is a factor, and that's one of the things that's really nice about having us over in Lincolnshire and our colleagues flying the same sort of drone over in Aberystwyth, because the genotypic data should be the same between the two. But then when you put it into the ground, you're going to get differences in growth. So we have a few repeats in that in our test sites, but hopefully being able to capture some stuff over 5 hours drive away in Aberystwyth, I think will help give us some confidence that we're seeing well-performing ones across multiple sites. But I think that is an interesting thing that we should have a look at, because that data is being recorded. It's just not being recorded as part of our project.
Fair enough. And what about collaboration with other applications? Because collecting point cloud data for plants could have other applications beyond Miscanthus. I don't know how to pronounce that.
Miscanthus, yeah, absolutely. I think especially with some of the other work packages, I don't want to take too much from them, but plant breeders in general are our project's goal, but we've picked Miscanthus because it's novel and because it hasn't had as much attention as other plants. So all the techniques we develop with this hopefully could be applied to breeders more generally, especially my colleague who's been trying to speak to plant breeders. They're very busy people. It's hard to get hold of plant breeders. and then a subset of that only focus on Miscanthus, you're looking at a very small subset of people. But if we establish some nice techniques with Miscanthus, I think that would be really exciting to expand it to further plants. Specifically from my area, we're taking a lot of techniques from wheat that have been done for phenotyping of wheat. But if you compare, for example, the sheer size of the Miscanthus to a wheat plant, there's a whole different range of challenges. So from the data collection, we might take some more techniques from other people, but in terms of the data processing and data application, I think it will feed back into plant breeding more generally, yes.
And Farzar, my understanding that your background is more engineering, and is that correct?
Well, my PhD was on spectroscopy for the Mars rover.
So physics.
Yeah, but any sort of robot out in the field collecting data, I'm interested in.
Fair enough. So what kind of challenges of data storage? Like we are collecting now, like at the end of the day, the end product is a height map.
Yeah.
But storing a point cloud is huge.
Yeah.
And like, do you guys work on multi-level or multi-resolution data or data compression, targeting these kind of applications?
Yeah, hopefully my other colleague, Dr. Yusu, would hopefully be able to do a talk maybe later in these series. He's done some really nice work, because when we first opened these last files, they would crash our computers a lot of the time. So we did some decimalization, we reduced the number of point cloud density, we find the areas that are interesting, and then we go back and look in higher resolution. But yeah, that is a big challenge. It's very easy. Well, I don't want to say it's very easy because this is what I do. But you could go out and collect all the data you want, but storing it and processing it is a real challenge.
Thank you. And I will repeat the message, which Amin usually present, say, please post your questions in the chat. We have 8 live audience. So we have, here's a question. Somebody answered our questions.
Yeah.
So the question is saying, from Hannah, she's asking, as this is a small pilot study, what challenges do you expect when implementing it at scale?
I think there's different ways of considering the scale. There are physical limitations of flying the drone. So we are limited by battery, we're limited by data. A much larger field than this, we would really struggle to get everything in a single flight. And the longer you fly, the more your weather conditions change. We used to be quite near to the Scampton Air Base, so we'd have to go and get permission to fly, and we'd have limited issues. But the drones are really nice because you could plant a lot more plants in that field and get a much greater coverage. So there are issues for scaling up, but I think the field sizes are okay. You just need to get more plants out there, but that's more manpower and more time. I think plant breeding is always limited by scale, but if we can get the data better, then they can focus the time that they have on maybe setting up larger trials. But yeah, thank you. That's a good point. We do really need to have a think about how it will expand further.
I have a question, if I could ask. At the beginning of the presentation, you just mentioned that you inspired from Southeast Asia for growing this Miscanthus.
Yeah.
But the thing is, because I lived in Korea, so over there, I mean, that's a huge difference in weather, in humidity and temperature. So how come you just found that this Miscanthus is appropriate for UK as well?
So yeah, I think it was originally brought over as a decorative plant. You know, I think it's one of these things where like Victorians brought it over and grew it. Sometimes you'll see them nice, sort of this nice big leafy thing with sort of a frond on the top, and you'll see that in a decorative setting. So they have been over here for a while now, and there's a bunch of different biofuel plants that have been explored. I think sort of willow trees, sorghum. There's all sorts of things that are like these sort of C4 grasses that have been explored. But Miscanthus has really started to tick up as a possible biofuel. So it's been brought over. We've seen it grow. It can grow here, but we want to make sure that with things like drones and AI, we can accelerate the process of making sure that it's better adapted to the UK environment. And also that it doesn't spread like some of the other invasive species, making sure that it is a useful species and a contained species.
Makes sense. Thank you. So, Ahmed, if you have any question.
I can go for it. It's a very interesting topic to me. One of the questions one of the comments during the talk, you mentioned about the software, which is closed source coming with this drone manufacturer. Is open source drones where you have more control on the software?
Yes, but they're not as good. It's the trade-off at the moment. Yeah, DJI stuff is really nice. It is really nice. But it is closed and it is a bit frustrating. So there's this extra step where we have to take the data, put it into our processor, and there's a license on that. I think unfortunately that's happening a lot in agriculture. That there's all these great tools, but they are slightly gate kept. So if we can show that it's worth doing with this LiDAR data, then maybe it's worth putting in resources into more open source. But in terms of usability, I can't complain. But yeah, I think that is something to worry about before putting all your eggs in this basket, is that there is this closed ecosystem.
I think we don't have any further questions from the speaker, so from the audience. So we would thank Ollie again for the very clear and interesting discussions and presentation he showed us today. Thank you, Ollie, for sharing your research.
Thank you.
Yeah, thank you so much. Thank you, Ahmed, for your help for this session. But before closing this session, I'm excited to announce that for the next session, which take place on next Tuesday, 27th of August at 2 p.m. This session, Dr. Michael Short from University of Surrey will present the mathematical optimization with surrogate and data-driven modeling for sustainable system, from efficient process synthesis to bias control optimization. So please enjoy us for next week for this presentation, and hope you guys see you soon. Thank you for joining.
Thank you, Goyal, and thank you, Ollie, and thanks to all who joined us today and asked questions. Thanks, Amit, for sharing.
Thank you.
Thank you.